Welcome to the Inner Ascent. Today we step into one of the most mysterious frontiers of modern physics, quantum entanglement. A phenomenon that suggests the universe is not a collection of separate parts, but a single, interconnected field. Here, distance loses meaning. Information moves without traveling. And the fabric of reality behaves less like empty space and more like a hidden web linking everything that exists. This episode invites you to explore what this means for matter, for time, and for consciousness itself. Let's begin the ascent.
Welcome to the deep dive. If you're here, you're looking for the shortest route to being the most informed person in the room, and today we are tackling a concept so profound, so counterintuitive, that one of its primary discoverers, Albert Einstein, dismissed it as nothing more than a trick of the math.
We are diving into quantum entanglement, this instantaneous invisible connection between particles. It's what Einstein famously called spooky action at a distance.
And it's not an exaggeration to say it challenges everything, right? Our deepest assumptions about separation, causality, even the very nature of space-time.
Everything. It forces a total rethink.
That's a huge scope.
Sure.
So our mission for this deep dive is pretty ambitious. We're going to start by laying out the philosophical paradoxes, the things that define the whole 20th century debate.
The famous EPR challenge.
Exactly. Then we'll move into the empirical world. We'll walk you through the definitive, hard-won experimental proofs of entanglement.
The loophole-free Bell tests, the big ones from 2015.
And from there, we'll get into this profound irony, why this instantaneous connection is absolutely useless for faster-than-light communication.
Right. But at the same time, it forms the bedrock of pretty much every quantum technology, from computing to cryptography.
And finally, we're going to leave the lab entirely to investigate something that sounds like science fiction. The fact that entanglement isn't just theory. It's happening right now, in us, in biology.
I mean, it's how a robin navigates. It might even explain how fast a caterpillar can turn into a butterfly. It's everywhere.
Okay, let's unpack this. Before we even get to the particles themselves, we have to start with the fundamental philosophical tension.
Right.
Why was the physics community not content just, relying on the math?
Right.
If the mathematics of quantum mechanics predicts every observable outcome perfectly, why did Einstein and the others care so much about what the real behavior of things was?
That's the core tension. That's what drove the entire debate. Mathematical mapping, being able to capture and predict your experimental data, that's necessary, but for a lot of physicists, it's just not sufficient.
It's not the whole story.
Not at all. I mean, if the math describes what happens, but it doesn't give you any insight into how or why the universe is built the way it is, if it forces you to abandon core concepts like an objective reality or locality,
then you haven't really explained anything.
Exactly. You haven't explained the nature of the universe. You've just created a really good rule book for the data.
So if quantum mechanics worked mathematically, the problem wasn't the equations. The problem was what the equations implied about reality.
Precisely. It forced a complete departure from classical lines of thought.
Yeah.
In the classical world, you could look at a tennis ball, you could list its properties, its mass, its velocity, its spin.
And those properties were real. They were definite. They belonged to the ball, whether you were looking at it or not.
Yes. And entanglement just radically destroys that whole notion of isolation. It suggests that two systems, miles apart, can fundamentally share a single state description. They can't be considered separate entities anymore.
To really grapple with entanglement, we first have to understand the inherent weirdness of the quantum world itself. And that always starts with the classic illustration of quantum probability, the double-slit experiment.
This is the one. This is the test that truly shattered classical intuition. When you fire tiny projectiles, let's say electrons, at a barrier with two parallel slits.
You'd expect them to act like tiny bullets, right? They should just land on the screen behind in two neat bands lined up with the slits.
That's what you'd expect, but they don't. Instead, you get this really complex interference pattern, lots of bands or stripes.
And that stripy pattern is the dead giveaway for waves. It's like ripples in a pond interfering with each other after they pass through two openings.
Exactly. The only way to mathematically account for this behavior is to describe the particles not as definite, localized objects, but as undulatory waves of probability.
Which is the concept of superposition.
Right. Before you observe it, the particle exists in a combination of all possible states. Its location isn't definite. It's, 30% here, 22% there, 48% somewhere else. Its spin is both up and down at the same time.
And this isn't just us being vague because we don't know. This is fundamental reality. And it's governed by a specific law, the Born rule.
Yes, the Born rule is what dictates the precise probability of observing any one of those outcomes. It confirms that the universe at this fundamental level is irrevocably probabilistic.
But here's the kicker.
Here's the kicker. The moment you decide to measure the particle, the act of observation itself, that whole diffuse wave function justice, it instantly collapses.
It goes from being a smear of possibilities to one single definite outcome.
One spot.
One spot. And that transition, that moment of collapse, that is the famous measurement problem.
It's the gap in the theory we still don't know how to fill. It is the great causal mystery, and it leads to these profound philosophical divisions. I mean, if you believe the physical world is fundamentally localized, you might lean towards something like spontaneous collapse theories.
Arguing that the wave function just naturally collapses on its own when a system gets complex enough.
Sure. Or, if you want to maintain the integrity of the math at all costs, you might gravitate toward the Everett or, the many worlds interpretation.
Where every measurement causes the entire universe to branch into countless parallel realities, and each one realizes a different possible outcome.
Right. But either way, we are forced to invent these incredible mechanisms just to explain how we get from quantum potentiality to the classical certainty we see every day.
And this is exactly where Albert Einstein drew a line in the sand. He believed that the quantum description had to be incomplete because it violated his two favorite principles, which we packaged together as local realism.
Local realism is basically the classical worldview, and you can split it into two restrictions. First, you have realism,
Which just says that every physical object has to have definite predetermined properties before we measure them. A ball is red, even if no one is there to see it.
Exactly. And second, you have locality. Physical objects can only be influenced by their immediate surroundings. And crucially, no information or influence can travel faster than the speed of light.
Entanglement seemed to just blow right through both of those conditions at the same time.
It did. And that's what led to the 1935 thought experiment he published with Podolsky and Rosen, the EPR paradox.
So the goal of the EPR paper wasn't to disprove quantum mechanics. It was to prove that it had to be an incomplete theory.
That's the key. They envisioned preparing a pair of particles, A and B, in an entangled state, say. Their total spin adds up to 0, and then you let them fly apart over vast distances.
And the genius of this setup is that Alice, who's measuring particle A, can instantly predict particle B's state with 100% certainty.
Correct. If Alice chooses to measure the position of her particle, A, she instantly knows the position of B. If she decides to measure the momentum of A instead, she instantly knows the momentum of B.
Because they're not really separate objects. They're still described by a single quantum state.
Exactly. And here's the logical trap they sprung on everyone. It's called the EPR criterion of reality.
This was their core logical weapon.
It was. The criterion stated that if you can predict the value of a physical quantity with certainty, and you can do it without in any way disturbing the system, then an element of reality corresponding to that quantity must exist before you even measure it.
Okay, so particle B is miles away. Alice measuring A can't possibly disturb B locally.
Right.
Therefore, since Alice can choose to predict either position or momentum for B with total certainty, particle B must possess definite simultaneous values for both position and momentum right now, before she even measures.
And that conclusion that B has simultaneous definite position and momentum is a direct, non-negotiable contradiction of the Heisenberg uncertainty principle.
Which says you can't know both at the same time for any system.
You can't. So Einstein concluded, quantum mechanics, which denies the existence of those simultaneous definite properties, it must be incomplete. There have to be some underlying hidden variables that are carrying this definite information along with the particles.
But the real emotional sticking point for Einstein wasn't just about the theory being incomplete, was it? It was the non-locality.
Oh, absolutely.
The idea that Alice's choice of measurement on A could instantly affect the state of B miles away. That's the famous spooky action at a distance.
He was deeply, deeply committed to the principle that physics must be local. He just believed that the real state of particle B should be completely independent of what measurement Alice chose to perform far, far away.
If that action was truly instantaneous, it would mean some kind of communication faster than light.
And that would just tear apart the entire foundation of his special theory of relativity. He couldn't accept it.
But Niels Bohr, great defender of quantum mechanics, he couldn't let that stand. So how did Bohr counter what seems like pretty flawless logic?
Bohr's response was, it was subtle. It relied very heavily on his conceptual framework of complementarity. He argued that the measurements of position and momentum are mutually exclusive.
There are complementary ways of describing the world.
Yes, the experimental setup you need to measure position is physically incompatible with the setup you need to measure momentum. You can't do both at once.
So you can't just combine the facts you'd get from two mutually exclusive experiments and pretend they apply at the same time.
Exactly. Bohr claimed that EPR's conclusion that particle B must have both definite position and momentum was fallacious. He said they were illicitly combining facts from different, incompatible experimental arrangements. For Bohr, the quantum state was the complete description, and for decades that's where it stood, a philosophical standoff, a battle of worldviews.
Okay, and this is where the whole debate explodes out of philosophy and into real empirical science. John Bell, in 1964, he gives us the intellectual tool to finally answer this question. Bell's theorem.
Bell's breakthrough was recognizing that this wasn't just philosophy, it was physics. It was testable. He showed that if local hidden variables, if Einstein's dream of predetermined, definite properties, were really responsible for the correlations you see,
then the results have to obey a strict statistical limit.
a very strict limit, a mathematical inequality. It's known as Bell's inequality.
So Bell basically built a mathematical fence. If any experimental result falls outside that fence, local realism is dead.
That's a perfect analogy. Any theory of local realism, it doesn't matter how complex its hidden variables are, it cannot produce correlations that are stronger than the ones allowed by Bell's inequality.
But quantum mechanics predicts something different.
Crucially, yes. Quantum mechanics predicts correlations that are significantly stronger than that classical limit. So if you can run an experiment and violate the inequality, you've proven non-locality is real.
This set the stage for decades of experiments. But those experiments proved to be incredibly challenging because, well, local realism is a very stubborn concept to kill.
Very stubborn.
We need to detail the technical hurdles, the famous loopholes that plagued all the initial tests.
Right. You have to ensure that no local realistic explanation can sneak back in through some back door. The first and most essential one is the locality condition. People often call it the space-like separation loophole.
So what's the requirement here?
It demands that the temporal and spatial separation between the measurement of particle A and the measurement of particle B has to be large enough that no causal influence, not even one traveling at the speed of light, could communicate between the detectors or the particles during the measurement process.
If the measurement happens too slowly, or the detectors are too close together,
then you haven't really ruled out a local signal traveling at or below the speed of light. Mathematically, you need the distance divided by the time to be greater than c for the measurement event itself.
if that loophole is open, local realism is still on the table because some hidden sublight signal could technically be coordinating the outcomes.
Yep.
Okay, what about the detection loophole?
The detection loophole was a huge problem in the early experiments, especially the ones using photons. Detectors are just not perfect, and a lot of entangled pairs get lost or go unobserved.
And that opens the door for what's called the fair sampling hypothesis critique.
Right. A local realist could argue, look, we don't need non-locality to explain your results, we just need detector bias.
So the claim is that the only particles that were detected were a statistically unrepresentative subset.
Specifically the ones that just happen to be locally correlated in a way that mimic the stronger quantum correlation. And they'd say all the lost undetected particles would have upheld the Bell inequality if you could have measured them.
So how do you close that?
You need incredibly high detector efficiency. For the most common formulation of the test, the CHSH formulation, your detector efficiency, has to be greater than or equal to 2/3. You have to catch enough of the particles to be sure that the ones you missed couldn't possibly account for the correlation you observed.
That's a serious technical hurdle. And finally, the memory loophole.
This is the randomness constraint. Alice and Bob, they have to choose their measurement settings. You know, the directions they measure, spin or polarization, using truly unpredictable means.
Because if the settings are predictable, or if they just change slowly.
A local theory could argue that the source of the entangled particles somehow knew the settings in advance and deterministically cooked the particle properties before they ever separated.
And as we touched on, true randomness is impossible if you assume local realism is true in the first place, because that assumes a deterministic universe.
That's the deep methodological paradox, isn't it? You're trying to test determinism, but the tools of your test have to rely on indeterminism. The best you can do is minimize this loophole by using incredibly unpredictable pseudo-random number generators, or even better, using light from distant quasars to determine the settings.
So any local causal link would have to stretch back billions of years.
Exactly.
Despite decades of effort, closing all three of these loopholes at the same time proved to be elusive. But then 2015 changed everything.
2015 was the empirical culmination of this entire 80-year debate. 3 independent experiments were published that succeeded in simultaneously closing the detection loophole and the locality condition.
And they delivered the strongest evidence yet against local
The
realism.
strongest evidence ever.
Let's look closer at one of them, the Henson et al. Experiment.
So Henson and his team used electron spins, which were trapped in diamond nitrogen vacancy centers. The big advantage of using electrons is that their entanglement is pretty stable and their detection efficiency is much higher, which makes the detection loophole a lot easier to close than with photons.
And they met the locality condition.
They did. They separated the measurements by over a kilometer and made sure the measurement time was faster than the light travel time between the detectors.
So what was their actual quantitative result?
They observed the CHSH test statistic, which is called S. Now, for local realism, S must be less than or equal to 2. It cannot go above 2.
And they measured.
They measured a value of S equals 2.24 plus or minus 0.20. This violation of the classical bound by several standard deviations it was hugely statistically significant. It told the community this correlation is simply too strong to be explained by any local realistic theory that wasn't, cheating in some way.
And the other 2 big experiments that year by Shalm et al.
Yeah.
And Justina et al., they used entangled photons.
That's right. And using these high-efficiency down-conversion sources and superconducting detectors, they confirmed similar, really strong violations of Bell-type inequalities.
Yeah.
All 3 experiments, using different systems, electron spins, photon polarization, they all converged on the same conclusion.
Quantum mechanics is fundamentally non-local.
It is.
So based on the current, rigorous, and statistically corroborated data, entanglement is real, and non-locality is the most accurate physical description we have. We have refuted Einstein's local realism.
That is the scientific consensus. And as you mentioned earlier, the only remaining logical exit for a really staunch local realist is to invoke the ultimate, untestable philosophical trump card, superdeterminism.
Let's just spend a moment on why this concept is so frustratingly outside the realm of testable science.
Superdeterminism claims that the universe is so fundamentally deterministic that not only were the outcomes of the particles predetermined from the Big Bang,
but even the choices made by the experimenters were predetermined. Alice and Bob's choice of analyzer settings, the output of their random number generators, all of it was fixed from the beginning of time.
Exactly. So there's no free choice in the experimental design. The universe was basically pre-programmed to produce a quantum result. It avoids the non-locality problem by just eliminating the possibility of a free, independent choice of measurement.
But since that idea can explain literally any result by just saying, oh, it was destined to happen, it's fundamentally unfalsifiable.
And therefore, it's not scientific. For all practical purposes, the Bell tests proved local realism is false.
Okay, now we get to the great constraint that saves physics from total chaos. If this connection is instantaneous, why can't we use entanglement to send information faster than light? Why can't Alice send an FTL message to Bob?
This is a consequence of something called the no communication theorem, and it basically maintains the sanctity of special relativity. So while the correlation between the particles is instantaneous, the transfer of useful defined information is prohibited.
Let's break down the mechanism of why that fails. If Alice measures her particle, why can't she force it into a state that Bob can then decode as a message?
It comes back to that probabilistic nature we talked about earlier. Alice cannot influence or force her particle A, to collapse into a specific state, like spin up. When she measures it, the result is intrinsically random. It's 50% up, 50% down.
She has absolutely no control over the outcome she observes.
None whatsoever. So if Bob is far away, the sequence of measurements Alice makes is just going to look like a completely random string of bits. And Bob, on his side, will see an anti-correlated but equally random string of bits.
So if Alice wanted to send the sequence 101, she can't manipulate her system to guarantee that outcome.
She can't. The universe remains intrinsically probabilistic, and that blocks any attempt at information encoding. The signal that would carry the information is just completely drowned out by the fundamental 50-50 randomness.
So the instantaneous correlation reveals information about the shared state.
But the lack of control over the measurement outcome prevents Alice from encoding a message.
There's a great analogy for this with cosmic demons in a pair of shoes.
It's a perfect analogy. When Bob opens his box and sees a left shoe, he instantly knows Alice received the right shoe. That's the instantaneous, non-local correlation.
Right.
But he cannot use that shoebox to send Alice a message because he had no way of controlling which shoe the cosmic demons placed in his box in the first place. The correlation exists, but the ability to harness it for FTL communication just does not.
It is so deeply ironic that this instantaneous phenomenon is constrained to sublight speeds. But that very constraint allows entanglement to be the core resource for a whole new generation of slower but profoundly powerful technologies.
Quantum information.
Right. And it all starts with quantum computing.
Entanglement is the fuel for the quantum revolution. So instead of classical bits, which are just 0 or 1, we use qubits. And thanks to superposition, qubits can exist as 0 and 1 at the same time.
But the real computational leverage comes when you entangle them together.
Absolutely. When you entangle qubits, their possible descriptive space expands exponentially. For n entangled qubits, the system has to be described by 2 to the power of n possible configurations, all simultaneously.
So just 2 entangled qubits is 4 possible states.
4 states. But if you scale that up to just 500 qubits, which is, a goal for a mid-range future quantum computer, the number of simultaneous configurations exceeds the number of atoms in the entire observable universe.
That is the key leverage. A quantum computer doesn't solve a problem by trying options one after another, like a classical computer. It explores this exponentially vast configuration space all at the same time.
Which makes otherwise intractable problems suddenly solvable.
And beyond computing, entanglement is the bedrock for the security of quantum key distribution, or QKD.
And this relies on another fundamental quantum rule, the no-cloning theorem.
The principle that you cannot perfectly duplicate an unknown quantum state.
Correct. So when Alice sends a quantum key, let's say a sequence of entangled photons, any eavesdropper, Eve, who tries to measure or copy that quantum state inevitably causes the wave function to collapse. That act of measurement changes the state. It's irrevocable.
So Eve leaves an undeniable signature on the data.
She does. Alice and Bob can simply check a portion of the key. If they find an error rate higher than what's expected from just noise, they know the channel has been compromised, and they just discard the key and start over.
That makes QKD fundamentally secure, even against future quantum computers, because the security isn't based on mathematical difficulty. It's rooted in the laws of physics themselves.
Exactly. And then we have these pure communication techniques like quantum-dense coding.
This sounds like a way to sort of cheat the system and send more information than classical physics allows.
It is, in terms of information density per particle. Classically, sending one particle can convey at most 1 bit of information. But if Alice and Bob pre-share an entangled pair in EBIT, Alice can then take her half of that EBIT and perform one of 4 specific operations on it.
And then she sends only her single qubit to Bob.
That's all. And when Bob receives it, he now holds 2 qubits, his original half of the entangled pair and the one Alice sent him. He performs a joint measurement on the pair, a Bell measurement, and based on the outcome, he can reliably extract 2 full bits of classical information.
So entanglement acts as a resource that doubles the classical information capacity of that channel.
It does.
And finally, the most sci-fi sounding application, quantum teleportation. And again, to be absolutely clear, we are talking about transferring information, not matter.
Crucially, yes, not matter. Quantum teleportation is the process of transferring an unknown quantum state. So the information encoded in a particle's spin or polarization from Alice's location to Bob's. And the key is, they never even need to know what the state is that's being transferred.
So how is this achieved without violating the no communication theorem?
They need 3 things. They need the particle whose state Alice wants to send. They need a shared entangled pair, the E-bit, and they need a 2-bit classical communication channel.
Like a radio wave or fiber optics.
Right, so Alice performs a specific Bell state measurement on her 2 qubits, the one she wants to teleport, and her half of the E-bit. This measurement instantly collapses the shared quantum state. The result of her measurement is one of 4 possible outcomes, which she then sends to Bob over that classical channel.
So the classical signal still limits the speed to the speed of light.
Correct. But once Bob receives those 2 classical bits of information, he knows exactly which one of 4 specific operations to perform on his half of the entangled pair. And that operation instantly converts his particle into an exact replica of the original quantum state Alice wanted to send.
So entanglement prepares the channel, but the classical signal delivers the instructions for reconstruction.
You've got it. It's like a fax machine for quantum information.
This deep operationalization of entanglement forces us to ask a much more profound question. What exactly is this non-local connection? Is it a thing? Is it a relationship? Or is it just a reflection of something deeper? This moves us into metaphysics.
It does. The standard interpretation of that Bell test violation often leads to what's called entanglement realism. Realists argue that entanglement is a genuine, irreducible feature of the world. It's a non-classical physical relation that links systems.
Meaning that separation is really an illusion at the quantum level.
Yes. But there are these compelling alternative views, like wave function anti-realism, which tries to resolve all the spookiness by just eliminating entanglement from fundamental reality entirely.
That sounds completely counterintuitive. How does that work?
Well, what they're being realistic about is the mathematical description of the universe itself, the wave function. But they say it's not defined the ordinary 3-dimensional space we live in, but in a much higher dimensional configuration space.
Okay, so if we look at reality through this lens, how does a high-dimensional space remove the problem of non-locality in our 3-dimensional world?
For a universe with, say, n particles, the fundamental reality is described as a physical field that exists in a 3n-dimensional space. And in that space, the wave function field itself is entirely local.
So all the seemingly instantaneous correlated behaviors we see in our ordinary 3 space, the entanglement, is just a reflection, a projection.
It's merely a reflection or a projection of a single, localized state that's evolving in that higher dimensional space. The spookiness isn't fundamental. It's an artifact of viewing a high-dimensional localized phenomenon through our limited 3-dimensional eyes.
So it maintains locality, but at the expense of our intuition about separation and individuality.
That's the price you pay. The consequence is a form of, well, ontological holism. What we call 2 separate entangled particles in 3 space are fundamentally just 2 highly correlated points on a single localized field in 3n space.
This idea that the spatial structure we perceive is a derived concept, it leads us to the most radical theoretical work in modern physics. The idea that spacetime itself is not a fundamental background, but an emergent property.
This is truly mind-bending. It's often rooted in models of quantum gravity, like the holographic principle. The theory suggests that the geometry of space-time, the distances, the curvature, the connections, may literally be stitched together from quantum entanglement.
So entanglement is the foundational connectivity of the cosmos.
It's the fabric. If entanglement is the fabric, then distance, or the lack of it, is the ultimate measure of reality. Research has shown these incredibly deep mathematical connections between geometric concepts in space-time and entanglement measures in the underlying quantum field.
And one of the key concepts here is something called entanglement entropy.
Entanglement entropy. It's a measure of the degree of entanglement between 2 regions of space. And what's really fascinating is how it relates to time.
Okay, how so?
Research simulating the dynamics of quantum fields has found that the growth and spreading of entanglement entropy across these fields mirrors the evolution of a universe in time.
Which raises the profound possibility that time itself isn't an external dimension, but a side effect of entanglement spreading. The arrow of time, our unidirectional experience of moving from past to future,
might simply be the entropic flow generated by entanglement maximizing itself across systems. The more entangled 2 regions become, the greater the elapsed time, effectively.
So if entanglement establishes spatial connectivity and its entropic growth drives temporal evolution, then the breakdown of entanglement in extreme environments, like the inside of a black hole,
could literally imply the breakdown of the geometry of reality itself?
that is profound cosmic theory. But we promise to pull this out of the cosmic and the computational and show that nature is using these quantum rules with ease right here on Earth. Let's talk about quantum biology.
This is arguably the most surprising area of entanglement research. I mean, we typically think quantum effects are fragile, that they require temperatures near absolute zero and perfect vacuums.
But nature has perfected using these effects in warm, wet, messy environments. And it starts with the quantum robin.
The European robin. It migrates thousands of miles, relying on the Earth's magnetic field. And yet, that field is unbelievably weak. It's about 20,000 times weaker than a refrigerator magnet.
How can a biological system possibly detect something so faint?
The mechanism relies on a biological compass built around entanglement. The robin has these specialized proteins in its eyes called cryptochromes. And when a photon of light hits the cryptochrome, it sets off a reaction that creates a pair of electrons with linked spins. It's called a radical pair.
So the photon generates an entangled pair right inside the bird's eye.
Yes. And the chemical state of that cryptochrome molecule is poised on this energetic knife edge, balanced by the spin of those two entangled electrons. The unbelievably weak direction of the Earth's magnetic field subtly interacts with these entangled spins.
It acts like a tuner.
It acts like a tuner. It subtly tips the balance of the entanglement, which in turn influences the subsequent chemical reaction.
That is a stunning mechanism. So the entanglement acts as an ultra-sensitive amplifier, allowing the robin's brain to essentially read the Earth's field direction by detecting a change in the concentration of a certain chemical.
It's the ultimate proof that nature exploits non-locality. It's a naturally occurring quantum sensor, and it's operating flawlessly at body temperature.
And it's not just navigation. Our own senses might be quantum mechanical.
You're referring to the quantum smell theory. The classical lock and key theory suggests that molecules fit into our scent receptors based on their shape.
But where does that theory fail?
It fails repeatedly when you deal with molecules that have similar shapes but vastly different odors. Or conversely, molecules with different shapes that smell identical. It just can't explain it.
So the alternative is that our noses aren't looking at molecules, they're listening to them, sensing their energy rather than their shape.
Exactly. The quantum smell theory suggests olfaction relies on molecular vibration. When a scent molecule docks in a receptor, an electron in that receptor molecule tunnels from one side to the other.
And to tunnel, it has to listen for a specific vibrational frequency in the scent molecule.
Right. If the scent molecule vibrates at the frequency the electron needs to borrow energy from, the electron can tunnel across the gap, and that triggers the receptor. Different molecular vibrations mean different tunes, which mean different smells.
That makes our sense of smell sound like a spectroscopic process. Is there hard evidence for this?
Yes, the deuterium experiments. Scientists created two versions of the same odorant molecule. One had normal hydrogen, which is just protons, and one where the hydrogen was replaced by its heavier isotope, deuterium.
Deuterium is twice as heavy, so it changes the vibrational frequency of the molecule, but it does not change its shape.
Exactly. So if the lock and key theory was right, the flies in the experiment shouldn't have noticed a difference.
But they did.
They absolutely did. Fruit flies were trained to distinguish between the two isotopes, and they could smell the difference with certainty. It's compelling evidence that vibration, a wave-like quantum behavior, is the crucial factor.
If we're discussing tunneling, we should probably define it fully. Quantum tunneling is this bizarre effect where a particle passes through an impenetrable energy barrier without ever going over it.
It's a purely non-classical wave-like behavior. It's a proven fact of nuclear physics. It's responsible for the fusion reaction in the sun. The particle just vanishes on one side and reappears instantly on the other.
And life, it turns out, is highly dependent on this ghostly action because classical mechanics is simply too slow.
It is. Many complex biological processes require enzymes to break down tissues or build new molecules, and that means moving protons around to untie or form chemical bonds. Classically, the protons would have to climb over an energy barrier, a sort of activation hill.
Which is a slow, thermally driven process. If the protons had to wait for enough heat energy to jump that barrier, life would be running in agonizing slow motion.
Precisely. The process of a tadpole transforming rapidly into a frog, that would be impossibly slow. Quantum tunneling allows protons to simply pass through the energy barrier, bypassing the time delay imposed by classical physics. It ensures biological reactions happen at the speed necessary to sustain life.
And the final, most profound implication of quantum mechanics in biology. Quantum tunneling may actually be a mechanism that drives evolution itself.
This is a powerful hypothesis. The quantum tunneling of protons across the double helix of DNA can cause an error in replication, a change in the genetic code, a mutation. The proton briefly tunnels to a non-standard spot on the DNA base, and if replication happens during that tiny moment of quantum distortion, the wrong base pair gets inserted.
So quantum mechanics could be generating the random variation that Darwinian evolution then acts upon.
That's the idea. And to test this, researchers did that substitution experiment again, this time using heavy water, where protons, which tunnel easily, are replaced by deuterons, which are twice as heavy and tunnel less easily.
If quantum tunneling is responsible for a chunk of the mutation rate, then using deuterons should lower that rate.
That's the key prediction. And the preliminary results did indeed show that the mutation rate in the bacteria prepared in heavy water was significantly depressed.
Which suggests that a significant component of the random variation necessary for evolution, and thus the speed of life's adaptation, may be rooted not in chemistry, but in the specific quantum mechanical behavior of protons.
Yeah.
Yeah.
It's a profound thought.
We have completed an incredible journey. From Einstein's philosophical rage against spooky action to the empirical triumph of the loophole-free Bell tests, confirming that non-locality is real and instantaneous.
And we witnessed the universe exploiting this non-separability for everything from the foundational architecture of quantum computing to the astonishing fact that a migrating bird's compass relies on entangled electron spins.
And that the speed of our own biological existence and perhaps even evolution is dictated by quantum tunneling. Entanglement forces you to completely redefine what it means for two things to be separated or isolated. The experiments consistently confirm that non-separability is a fundamental, universal feature of the world.
So if non-separability is a fundamental truth and every part of the universe is interconnected at the deepest level, the complete opposite of the classical idea of isolation, what does this universal interconnectedness imply for future research into causality and integrated systems, even with the knowledge that we can never transmit an FTL message?
That profound constraint, the no communication theorem, it tells us we can't send a signal. But the existence of non-locality tells us that the systems are not truly separate.
And that's the starting point for the next paradigm shift. Researchers are actively trying to integrate these concepts into new frameworks, exploring connections between entanglement and, say, the nature of conscious experience.
Echoing Schrödinger's much earlier insight that at the root of reality, the mind and the world are one.
It pushes physics into genuinely new territory. It's about how integrated, non-separable systems truly function and what novel causal relationships might arise from that foundational interconnectedness. It suggests that while the age of finding new stuff might be slowing, the age of discovering new relationships between the stuff has only just begun. It remains the ultimate puzzle left to explore.
You've been listening to The Inner Ascent, where growth begins from within. If today's reflection resonated with you, consider sharing it or revisiting it later. Until next time, stay aware, stay curious, and keep rising.